So students, welcome to the session. We will start the session of matrices again. Actually, before starting this session, let me classify the portion of matrices is being divided in two categories. Portion 1, that is what we have already discussed. In that portion, we did what? Addition of matrices, then how matrices are subtracted, then how they are multiplied, and few other properties. The remaining portion of the matrices is somehow dependent on the concept of the determinant. That is why before starting the session 2, the second portion of the matrices, we discussed a session on determinants. So we all are well versed with the concept of the determinant and how we can determine the values of the various determinants, so we can proceed the remaining portion of the matrices in this session, right? So we will begin this session with a new term that is known as transpose of a matrix. Let us have its formal definition, which is given in every book. Let A is equals to Aij, it's a simple or general notation of a matrix. Let A is equals to this be a matrix of order m by n. Then the matrix obtained by swapping the rows and columns of a matrix is called the transpose of a matrix. It is denoted by A prime, or in some books A raised to the power t. T simply refers the transpose, right? So this is the formal definition of transpose of a matrix. So what does it mean actually? If you have given any matrix, the first thing is what? The matrix may be square or it may be rectangular. There is no restriction on the matrix. So if you have given any matrix and you want to find out its transpose, what you have to do? Simply rows and columns of the given matrix must be interchanged together. Clear? If you have given a matrix and the transpose of a matrix is obtained by interchanging the rows and columns of a matrix. But be careful, when you are interchanging the rows and columns, the order of the rows and columns must be preserved, because matrix is an ordered structure of some objects or some numbers arranged in certain number of rows and columns. So order of the rows and columns must be preserved means what? If you are taking the first row should be interchanged to the first column. Second row should be changed or interchanged with the second column, and then third row should be interchanged with the third column. So by doing this operation, you can always find out the transpose of any matrix. For example, let us see, this is a matrix, right? And we want to find out its transpose, and AT, this is its transpose. See what we did here. I have highlighted the rows of A in three colors. The first row red, second row blue, and the third row is green. See what we did, rows and columns are interchanged to get the transpose of any matrix. This is the basic definition. So see, the first row of A is 1, 4, 2, 9, which is highlighted by the red color. The first row must be converted or interchanged with the first column. Look at here. This is your first row of red color, and this has been converted to the first column of the transpose, right? That is why I highlighted it by red color. Now the second row is what? Second row is of blue color. The second row should be interchanged with the second column. See this, right? Clear? Likewise, the third row is of green color. It has been interchanged with the third row, right? What does it mean? Simply, to A is any matrix, to find out its transpose, what we did, rows should be converted to columns. This is the approach. So whenever you want to calculate the transpose of any matrix, simply rows and columns of a matrix are interchanged together. By preserving their orders, you will get a new matrix that is called as transpose of the given matrix. Say A is equals to this matrix, this is a matrix having one row. We can also call it as a row matrix. So if it contains one row, then this row 2, 3, 5 must be converted or interchanged to the column, that is AT will be the matrix having one column with the same elements. Elements will remain the same. We are not going to change even a single element. Only rows and columns of a matrix should be interchanged to get a new matrix, and that matrix is being denoted by AT, or we call it as a transpose of a matrix. Now we can have some properties of the transpose of a matrix. A number of properties of the transpose of a matrix are already discussed, are given. We will discuss here few. Property 1 is what? AT of T is equals to A itself. What does it mean? See, it shows if A is a matrix and you are getting its transpose by as AT by using the process of getting transpose. So if AT is transpose of this, you can again take its transpose, you will get the matrix A itself. This is property 1. Means transpose of a matrix is the matrix itself. Clear? This is property 1. Take an example. What is here? A is given as the matrix 5, 2, 3, 7, minus 1 and 5. This is our matrix. I have told you to get the transpose, the matrix may be square or it may be rectangular. There is no restriction, right? The matrix may be of any type. Say A is this is a rectangular matrix. So to find out its transpose, what we will do? This is the first row. This row should be converted to the first column, that is 5, 2, 3. This is the second row. It should be converted to the second column. So this is the transpose of this. Now AT is in fact the transpose of A. AT is also a matrix. We can also find out its transpose. So if we take transpose of this transpose matrix, what you will get here? We will use the same process. Rows should be converted to the column. So here 5, 7 is the first row. So it will be 5, 7 will be the first column. 2 minus 1 is the second row. So 2 minus 1 is the second column. 3 and 5 is the third row. So 3 and 5 is the third column, and this is what? This is the matrix A itself, right? I have shown here A is equals to 5, 2, 3, the first row highlighted by the red color. Its transpose, this first row will be interchanged to the first column of AT. See here 5, 2, 3. Second row is of normal color black, 7 minus 1, 5. It will be interchanged to the second column of AT, 7 minus 1, 5, and again take its transpose to get the original matrix itself. So transpose of a transpose itself matrix gives you, right? And this is true for every matrix, not only this. It's true, this property is true for all matrices, whether the matrices are square or rectangular. Property 2 is what? For any two matrices A and B of the same order, right? A plus B transpose is equals to A transpose plus B transpose. What does it mean? If we have two matrices A and B and we add up to get A plus B, and if we take the transpose of A plus B, so the transpose of A plus B will be equal to transpose of A plus transpose of B. This is what this property refers to, and it has been explained very clearly by this example. Say this is a matrix A, right? Then its transpose is this, right? See, first row of A has been interchanged to the first column of AT, that is of red color. Second row of A, that is of blue color, has been interchanged to second column of AT, and third row I have taken is of green color. It has been interchanged to the third column. So we will get AT. Likewise, this is the matrix B. Find out B transpose, that is BT. Again the same process. The first row of B is of red color, that is 2, 1, 3, must be interchanged to the first column of BT, that is 2, 1 and 3. Second row of B, that is of here blue color 3 2 2, it should be interchanged to the second column, and the third row 6 5 1, it should be interchanged to the third column. So AB is there. We can find out their transposes, that is AT and BT. Now what we will do, find out the sum of A and B first. And you know how two matrices are added and subtracted. You know that two matrices can be added only if they are of the same order. So A and B both are matrices of order 3 by 3. So we can add up. A plus B is equals to, this is A, this is B. Add up these two matrices. Addition of matrices means we should add up their corresponding elements, right? So 1 plus 2 is 3, 4 plus 1 is 5, 7 plus 3 is 10, right? So add up all these elements, you will get a matrix like this, right? So this is a matrix A plus B. Now find out its transpose. Clear? How we can find out its transpose? This is a matrix. A plus B is this. Find out its transpose means rows and columns should be interchanged again. See here, the first row of A plus B is 3, 5, 10. So it should be converted in the first column of A plus B transpose. The second row of A plus B should be converted to the second column of A plus B transpose. Likewise, the third row of A plus B should be converted to the third column of A plus B transpose. Right. So A plus B transpose we can obtain, and this is matrix this. Now see, A plus BT is this. Now find out AT plus BT. We have A transpose, we have B transpose, and we can add up these two matrices, and the sum of these two matrices is coming out to be this. So see, this matrix and this matrix both are same. Therefore, sum transpose of the sum of two matrices is equals to their sum individually. A plus B transpose is equals to A transpose plus B transpose, right? Now let us take another property. If A is any matrix and K is any scalar, K is any number, then Ka of transpose is equals to Ka transpose. Means if A is a matrix and we multiply any matrix by any number, we will get Ka. It is known as scalar multiplication. If we find out the transpose of Ka, it must be equals to K times of A transpose. See, you can verify this by this example. A is this matrix and AT is this, right? The first row 1, 2, 3 should be converted to the first column 1, 2, 3. The second row 2, 1, 3 should be converted to second column of AT 2, 1, 3, right? A is this, AT is this. Now find out Ka. Ka means multiply the matrix by K. So multiply the matrix by K means all the elements of the matrix should be multiplied by K. So we will get here K twice K, 3K, twice K, K and 3K. Now this is also a matrix. Take the transpose of this. So its transpose will be what? First row K, twice K and 3K, it will be converted to the first column, right? Second twice K, K and 3K, it should be converted to the second column. So this is Ka transpose. That is the left hand side. Now what is right hand side? The transpose of a matrix should be multiplied by K. This is the transpose. Multiply this matrix by K, you will get this. So this matrix and this matrix, you can see both are same. So this is property 3. Ka of T is equals to K times A transpose. The next property is what? For any two matrices A and B, we have AB transpose is equals to B transpose A transpose. If two matrices are multiplied together and we take the transpose of this product, this is equals to B transpose and A transpose. This is a very important property. The transpose of the product of two matrices A and B is equals to the product of their transposes but taken in reverse order. Not A B of transpose is not equals to A transpose into B transpose. Now you can verify this property by these two matrices. Say A is this, we have taken the matrix A is this, B is this, right? So what we want to show, that find out the product AB. AB, the product AB is coming out to be this 11, 23, 7 and 22. This is the product of A and B. Now take the transpose of this product, because AB transpose means first find out the product AB and then take its transpose, right? So AB is there, this matrix, right? Now its transpose is the first row 11, 7 should be converted, the first column should be converted to the first row 11, 7 and second column should be, rows and column should be interchanged. So AB transpose is this matrix, right? Now A is this, find out its transpose AT, clear? If A is 1, 2, 3 as a first row, then AT will have 1, 2, 3 as a first column. And if A is having 2, 1, 3 as a first row, then AT will have 2, 1, 3 as a first column. So this is AT. Likewise, this is BT. Here, the first column of B is 0, 1, 4. So the first row of BT must be 0, 1, 4. The second column of B is 2, 3, 5. So the second row of BT should be 2, 3, 5. So this is how we can calculate A transpose and then B transpose. Now multiply B transpose with A transpose, right? This is B transpose and this is A transpose. We know how the two matrices are multiplied. This is all we have discussed in the last session. So find out the product of these two matrices, and the product of these two matrices is coming out to be this. And if you look at this matrix and this matrix, both are same. Therefore, AB transpose is equals to B transpose into A transpose, right? Now, after having all these properties, with the help of the transpose and its basic properties, we can define a variety of new matrices. And among those variety of matrices, two matrices are very important, which play a very prominent role in the development of the theory of matrices. And these matrices are symmetric and skew-symmetric matrices, right? So before defining the symmetric and skew-symmetric matrices, you know what is the meaning of symmetry? Symmetry simply refers what? If you have any object and if you divide any object in two equal parts, then both parts should be replica of each other. Means both parts should be same in all respect. This is the meaning of symmetry. Are you getting the point? If you take a circle, if you take an example of a circle, this is a circle, and if you divide it in two parts, so the two parts will be verbatim, photostat of each other, right? Then such an object or such a figure is known as symmetric figure, right? So the same concept of symmetry will be used here in case of matrices. Let us define the symmetric and skew-symmetric matrices first. The matrix A is said to be symmetric if A is equals to AT, right? If a matrix is called symmetric if A is equals to AT, means a matrix is called symmetric if its transpose is equals to matrix itself, right? Before explaining the concept of the matrices, throughout from here onwards, every matrix must be considered as square matrix. We will not consider rectangular matrices now onwards, right? So no need to mention a square. A square word is understood. Only square matrices can be symmetric or skew-symmetric, right? I have mentioned it here. Look at the remark finally. Only square matrices are symmetric and skew-symmetric. So in the definition, in some books you may have a definition like this: a square matrix A is called symmetric if A is equals to AT. Yes, this is also correct, because only square matrices are symmetric. A is equals to AT means what? A is written as, you know, Aij, right? And if we calculate its transpose AT, so transpose means rows and columns should be interchanged. And here in Aij, I denotes the rows and J denotes the column. If you recall the beginning of the session of the matrices, Aij, I, the first subscript denotes the rows and second denotes the column. So if we are getting its transpose, rows and columns are interchanged. So this can be written as Aj. And definition is what? A matrix is symmetric if A is equals to AT, means Aij must be equals to Aji. You can understand this definition or this definition, both are equivalent, right? So simply a square matrix is said to be symmetric if its transpose coincides with the matrix itself, or in other way you can also define it like this: Aij is equals to Aji for all values of I and j. Clear? Now let us understand it by example. Let us see, this is a matrix A. I have taken this matrix as A. A is equals to 1, 3, 7, 3, 2, 5, 7, 5, 6, right? We want to check or we want to examine whether the matrix A is symmetric or not. So what we will do, we simply find out its transpose. So see, what is the transpose? AT. Transpose means the rows and columns should be interchanged. The first row of A is 137, so it should be treated as 137, the first column of AT, right? The second row is 325, so it should be taken as 325, the second column of AT. The third row is 756, so it should be taken as 756 as third column of AT, right? So this is A and this is AT. Now what is the definition of the symmetric matrix? If A is equals to AT, see what is AT? 137, 137, 325, 325, 756, 756. So A is equals to AT. This implies the matrix A is symmetric. Clear? See here, I have taken this matrix A like this. This is a matrix A. Then we have written here AT, right? AT and A both are same. Therefore, the matrix A is symmetric. What I told you in the beginning, symmetry means if an object is being divided in between in two parts, two equal parts, then both the parts must be replica of each other. This is the meaning of symmetry. So see, only square matrices can be divided in between two parts. Rectangular matrices cannot be divided, and a square matrix can be divided in two equal parts through its diagonal elements. See, in this matrix, the elements which are of black color 1, 2, 6, they are the diagonal elements. See, they are the diagonal elements. So we can draw or we can divide this matrix through this diagonal elements exactly in two parts. One upper part of the diagonal, two the lower part of the diagonal. Now look at the upper and lower part, they are having same elements. In the upper parts, what we are having, the elements is of red color 375, and look at the below the diagonal 375. So this diagonal behaves like a mirror, right? The diagonal behaves like the mirror. 375, they are having the same image 375 in the lower part. This is the meaning of a symmetric matrix, right? So what does it mean? Diagonal elements should divide the matrix in two parts, and both parts, whether the part lies above the diagonal or below the diagonal, they must have same elements. Then the matrix is said to be symmetric. Otherwise, you can check if the transpose of a matrix is equals to matrix itself, it will be treated as a symmetric matrix, right? Second case is what? Skew symmetric matrix. In a similar way as we define the symmetric, a square matrix is said to be skew symmetric if A is equals to minus times of its transpose, right? Clear? If A is equals to minus times of its transpose, see, if A is written like this, Aij is equals to A, and Aji will be what? Minus times of Aji, because At is the transpose of this. If we take I is equals to J, for example, in this equation I and J both are same, so how we can write it? Aii will be equals to minus Aii, because I and J both are same. So transfer this from right to left, we will get here Aii is equals to 0. So this implies Aii is equals to 0. Aii means what? See, if I is 1, we will get A11. If I is 2, you will get A22. If I is 3, you will get A33. Now look at the matrix A11, A22, A33. They simply represents the diagonal elements of a square matrix. So what does it mean? A square matrix is called skew symmetric if this condition is satisfied, that is A is equals to minus At, and from this condition what we conclude, Aii is equals to 0 means what? This shows that all the elements along the principal diagonal of a skew symmetric matrix are 0. Clear? Aii is equals to 0 means what? This shows that all the elements along the principal diagonal of a skew symmetric matrix are 0. See, let us take this example. 0, 0, 0, they are the diagonal elements which are of red color. See, the diagonal elements are the elements along the principal diagonal must be 0, right? And what is left? The elements lying the above diagonal and elements lying the below diagonal. What happens in symmetric case? In symmetric matrix, the elements along the elements lying above the diagonal and elements lying below the diagonal both are same. But if the elements lying above the diagonal or elements lying below the diagonal are negative of each other, then the matrix is called skew symmetric. Means if the elements above the diagonal all are positive and the elements below the diagonal all are negative, but the elements should be same, and vice versa. Vice versa means if elements below the diagonal are positive and elements above the diagonal are negative, but the elements should be same, then such a matrix or such matrices are known as skew symmetric matrix. Look at this. 0, 0, 0 is the diagonal elements, right? The elements above the diagonal are 2, 5, 3, right? So the elements below the diagonal must be minus sign, but the element should be same. See, 2, this is minus 2, this is 5, this is minus 5, this is 3, this is minus 3. Clear? This is how we can understand the concept of symmetric and skew symmetric matrices. And finally, as I have told you, the concept of symmetric and skew symmetric matrices is valid only for square matrices, not for rectangular matrices, right? You can note it as a remark. Square matrices are symmetric and skew symmetric. Let us see how you can write down a symmetric matrix. Let me explain a method other than the approach. For example, if you want to write down a symmetric matrix, see, A is equals to what? If you want to write down a symmetric matrix of order 2, take any element here 1. If you have taken here 3, then 3 should be taken here, right? And here you can take any element 5. So this is a symmetric matrix. Clear? If you take here 1, it's your choice. You can take any element here. Here you have taken 3. It's also your choice. You can take any other element, but the element which you have taken here 3, the same element you must take here. And this is diagonal element, you can take any element. This is a symmetric matrix of order 2. See how you can write down a symmetric matrix of order 3. Take element 1. right? Here you have taken 3 and 5. So this is the first row of the matrix 1, 3, 5. So what you should do, the first column should be same 1, 3, 5. Clear? The first row and first column should be same. Now here take the second diagonal element. So you have taken here 4. Now here you have taken 6, then you should have 6 here. And here you can take any element of your choice. This is also a symmetric matrix. See, 1, 3, 5, the first column and first row is same. Take the second diagonal element 4, 6 here, 4, 6 here. This is 5. Clear? So this is how you can write down a symmetric matrix of order 2 and order 3 by your own intuition. Likewise, if you want to write down a skew symmetric matrix, see how we can write it. A skew symmetric matrix of order 2, for example, you know, for a skew symmetric matrix, the diagonal elements must be 0. Say I have taken this 0, 0. They are the diagonal elements. What is left? If you have taken here 5, then it should be minus times of 5. So whatever element you will take here, the element below the diagonal should be negative of this, and vice versa, right? Likewise, if you want to write down a skew symmetric matrix of order 3, so this is 0, this is 0 and this is 0. They are the diagonal elements, right? For a skew symmetric matrix, the diagonal elements must be 0. Now here we have taken say 2 and 3. See, they are the elements above the diagonal. So if this is 2, 3, here we should get minus 2, minus 3. Clear? Now it's your choice. Here if you are taking say 5, then here you should get minus 5. So this is a skew symmetric matrix of order 3. So this is how you can understand the definition and the process of writing down a symmetric as well as skew symmetric matrix of order 2 or order 3, right? So before proceeding the numerical exercise or questions, let us have some basic properties of the symmetric and skew symmetric matrices. Property 1 is what? Sum and difference of two symmetric or skew symmetric matrices is again symmetric and skew symmetric. What does it mean? If you have two symmetric matrices A and B, if you find out their sum, A plus B, or their difference, A minus B. So A plus B and A minus B both are symmetric. Likewise, A and B are skew symmetric matrices, then A plus B as well as A minus B both are skew symmetric matrices. So students, I will advise you one thing, please verify all these properties yourself by taking the suitable examples. Take two matrices, sum of these two and see whether the sum of the two matrices is coming out to be symmetric, sum of the two matrices is coming out to be skew symmetric. Likewise, their differences are coming out to be symmetric, their differences are coming out to be skew symmetric. Property 2 is what? If AB are two matrices such that AB is equals to BA, then the product AB is symmetric, right? We all know that the commutative property is not valid for matrices in case of multiplication. So if we take A and B are any two matrices, then their product AB need not be symmetric, but AB will be symmetric if AB is equals to BA. This is the meaning of this property. Means if A and B are any two symmetric matrices, then their product AB will be symmetric if AB is equals to BA. Property 3 is what? If A and B are two skew symmetric matrices and AB is equals to minus BA, then the product AB is also skew symmetric. In the same way, if we take two matrices A and B, A is skew symmetric, B is also skew symmetric, then the product AB need not be skew symmetric, right? But the product AB will be skew symmetric if the condition AB is equals to B minus BA is satisfies, anti-commutativity. This is the property of commutativity. Property 3 is what? If A is symmetric matrix, then A inverse is also symmetric. matrix we haven't yet studied, so we will take up the case of matrix later. But if A is a symmetric matrix, we will find out the inverse in next few slides. So whenever the matrix A is symmetric, its inverse is also symmetric. For if matrix A is symmetric, then A raised to the power n is also symmetric. N is any integer. Means for any matrix which is symmetric, if you will multiply the matrix with itself any times, you will again get a symmetric matrix. If A is symmetric, then A square is symmetric. If A is symmetric, then A into A 5 times, A5 is symmetric. So like this, A into A n times, An is also symmetric. Property 5 is what? Determinant of a skew symmetric matrix is always non-negative. The determinant of a skew symmetric matrix can never be 0. And the last is what? The diagonal of skew symmetric matrix consists of 0 elements, and therefore the sum of the elements in the main diagonal is equals to 0, right? So these are the few properties which we can use whenever required in any solution of a given question, right? Let us take an example first. If A is a matrix, then AAT and ATA are symmetric matrix. What this example actually shows, say, if A is any matrix, we are not having any condition with A. A may be square matrix or A may be rectangular matrix. But be careful, only square matrices are symmetric as well as symmetric. But for transpose, we don't have any condition. We can find out the transpose of a square matrix as well as a rectangular matrix. So what is the question here? If A is any matrix, A is not specified here whether it is rectangular or square. It may be rectangular or it may be square. So if A is any matrix and we find out its transpose AT, this is a matrix, we find out AT, then if we multiply A with AT or AT with A, this is a symmetric matrix and this is also a symmetric matrix, right? A into A transpose and A transpose into A both are symmetric matrices. See, this is how you can construct a symmetric matrix by using this property. Means whenever you have given any matrix and you want to construct a symmetric matrix, find out its transpose AT, multiply A with AT or multiply AT with A. In both the cases, you will get a symmetric matrix. Say, this is A and this is its transpose AT, right? Now, multiply A and AT, the product of matrices we all have discussed in detail. I cannot discuss the process of multiplication here again. This is A, this is AT, A into AT, multiply this matrix with this. The product of these two matrices, it is mentioned here in detail, it is coming out to be this matrix, right? 14, 32 as a first row, 32 and 77 as a second row. See, 14, 32, 32 and 77, this is a symmetric matrix. Verify itself. This is symmetric because if you calculate its transpose, it will be equals to matrix itself. Now we can change the order. A multiplied by AT is symmetric. Now calculate AT with A. If transpose is multiplied with the matrix itself, so as usual, this is the transpose, this is the matrix A, and the product of these two matrices is a matrix of order 3 by 3. See, this is also a symmetric matrix. 17, 22, 27, the first row, 17, 22 and 27, the first column is same. Clear? 29 and 36, 29 and 36. Clear? But you calculate its transpose and then see its transpose will be equals to the matrix itself. It will verify that the given matrix is symmetric. So, student, I think I should stop it here and I will continue some interesting questions or exercise in the subsequent text. So, thank you very much.